Hello everyone, welcome to this video. So in today's video, we'll be solving the problem power of 4, and this is the problem of the day on Leetcode. And this is a pretty easy question. You could solve by using a while loop and all, but the key thing is what are the concepts that are we actually using to solve this problem. So it's like there is something new to learn if it's if it's the first time for you people to use bit manipulation concepts to solve this problem. So you can use anti-logarithms things as well, but this is a very easy, very peculiar method and also very time efficient method. Like dealing with bits is a time efficient thing, and so is the reason. So what does this question say? Given an integer n, return true if it's a power of 4. That's it, otherwise return false. And integer n is a power of 4 if there exists an integer x as that n is equal to 4 power x. All right, so n equal to 16, 4 square, n equal to 5, it's not a power of 4, so it will return false. N equal to 1, it's true because 4 power 0. So n can go up to minus 22 power 31 to 2 power 31 minus 1. So you could just limit off cut off the range of n here itself, because you can never have the negative results. All right, so you cannot never have negative results as the power of 4. So that is the reason the very first condition that I mentioned in the question is return n greater than 0. All right, n greater than 0 is the very first condition, that's for sure. If the value of n that's given is less than 0, then at the very first moment we can return false. Right, so follow up is, could you solve it without loops or recursion? That is the key thing here. All right, and what are the second two things? That is what we'll be seeing here. So if you could just examine the powers of 4. All right, so what are the powers of 4? 1, 4, 16, 64, and what are the other stuff? 256. All right, so 16 4, so 64 4s. All right, and okay, let me do one thing. Yeah, 1 4 16 64 256. So if we write these in bits, all right, if we write this in bits, so I'll be using 8 bits. So 0 0 0 0 0 0 0 1. All right, and 4 0 0 0 0 0 1 0 1. Oh, okay, 0. And 16 0 0 0 1 0 0 0 0. Right, so 1 2 4 8 16. Fine. And this one 0 1 0 0 0 0 0 0. All right, and 256. Okay, I'll be using another 0 here. Here 1 0 0 0 0 0 0 0 0. All right, so this is it. So if you can just see the pattern carefully, you see that here it is first index, here it is third index, here it is fifth index, here it is seventh index, here it is ninth index. All right, so ninth position, you could say not index, position, first position, third position, fifth position, seventh position, ninth position. So what do you observe here? You see that in all the powers of 4, just there is only one set bit. There is only one set bit, because 4 is ultimately the power of 2. So power of 2, in the sense, it will be only valid if there is only one set bit in the whole binary representation. And the key point to notice, they are at the odd position: first position, third position, fifth position, seventh position, ninth position. All right, so there are two things to be checked. First thing is, there is only one set bit, only one set bit. All right, one set bit. Second thing that you need to check is only one set bit, and second thing that you need to check it, the set bit is at odd position. Set bit is at odd position. All right, set bit is at odd position. Now to check the very first condition, what are we using? n minus 1 should be equal to 0. N and n minus 1 should be equal to 0. Why is that the case? Okay, let us take this example 4 itself. Okay, so if we take 4, what's the binary representation of 4? 4 is, I'll be using a different thing. 4 is, so we'll just write the same thing. We'll just use 8 bits, not an issue. 0 0 0 1 0 0. Okay, and now what is n minus 1? That is 3. What is the representation of this? 0 0 0 0 0 0 0. Okay, 1 1. All right, so when you subtract a 1 from a set bit, all right, when you subtract a 1 from a set bit, all the corresponding numbers, like corresponding numbers to the right all the zeros will be turned to 1, will be converted to 1. Similar is the case if you take 16. What is the representation of 16? 0 0 0 1 0 0 0 0. All right, is it correct? 0 0 0 1. Okay, and 0, yeah, it's fine. Now what is the binary representation of 15? That is n minus 1, 16 minus 1, 15. 0 0 0 0 1 1 1 1. If you can if it's required, you can even check. This is 8 4 2 1. What is the sum? 15. All right, so this is how the representation works. So when we do the end of these two values, all right, when we do the end of these two values, 0 and 0 and 1 0, 0 and 1 0, 1 and 0 0, and all these are zeros. So finally you end up getting 0. It's same is the case here as well. 0 and 1 0, 0 and 1 0, 0 and 1 0, 0 and 1 0, 1 and 0 0. So again it's completely 0. So if it is having only one set bit, then n end operation with n minus 1 would result in 0. That is for sure. Okay, so if this is the case, and then this would be valid. This would be valid only if we have one set bit. All right, so if this is this is also fine. If I find that yes, I found only one set bit because n and n minus 1 resulted me 0. Okay, then I've got that my binary representation of that particular number is only having one set bit. Okay, fine. Now the only task that is left for me to check is if that set bit is at odd position or even position. If it's at odd position, then only it is the power of 2. If it's at even position, then it's not a power of 2. So how do I check it? So for that reason, let us see this particular 16 itself. All right, so 16. Okay, 16, the binary representation of 16 is 0 0 0 1 0 0 0 0. All right, now if I have some number like this, if I have some number which have at the odd position, okay, at the odd position if I have 1, and at even position if I have 0, 1 0 1 0 1 0 1 0. Okay, sorry, I told odd position once. All right, so 1 0 1 0 1 0 1 0. Okay, I'll be framing a number says that at odd positions the set bit would be there, and at even position the set bit would not be there. Okay, so at even position it would be 0, and at odd position there is a set bit. So if in that is the case, when I do the end operation, 0 and 1 I get 0, 0 and 0 I get 0, 0 and 1 again 0, 0 and 0 0, 1 and 1 1, 0 and 0 0, 0 and 1 0, 0 and 0 0. So I get a 1, I get a set bit, or I could say I get some answer that is greater than 0 if I have a set bit at odd position. Okay, if I have a set bit at odd position, first condition I'll check is if my binary representation of that number is only having one set bit. Okay, that is fine. I got to know that it's having only one set bit. Now I need to check if it's at odd position. So to check that, I'll be doing a AND operation with a binary number such that it has only set bits at odd position. Okay, only odd position. This is fifth position, this is third position, this is first position, this is seventh position, only at odd position. And if I do the AND between those, I'll be getting greater than 0 only case if my original number, that is the first number, like the original number that I'm working on, has a set bit at odd position. If in case it has a set bit at even position, let us assume it is 0 and it is 1, then this would result as 0. All right, so it will only result greater than 0 if the set bit is at odd position. It is at odd position. So that is the reason we are doing n. So for the second condition, we are checking n and n minus 1 is resulting in 0 or not. Yes, if this is also satisfying, then the third condition that we need to look at is n and 0x55. So what does this mean? 0x55, 0x. So 0x55 says that, like 0x particularly says that, okay, says that it is a hexadecimal number. All right, hexadecimal number. And how do we represent things here? 0 is represented as 000, 1 is represented as 0001, similar is the case, 2 is represented as 0010, and it goes on till 9. It's represented as 1001, and now A, okay, A is 1010, B is 1011, C is 1100, D is 1101, E is 1110, and F is 1111. All right, so this is like this is 10, this is 11, this is 12, this is 13, and this is 14, and then this is 15. All right, so this is the hexadecimal 16, right? So 16, so we have 15 things here. So we are like 0x and now if we have 5 here, so this is represented as 0101. So 0x, if we represent 5, okay, 5 in this here, so 0x5 represents this like 0x0101. If I represent this for 8 times, so 5 5 5 5 5 5 5, so 0101 again 0101 0101, this goes up. So 4 times 8, that is equal to 32. Okay, so because it is an integer range that has been given, 2 power 31 minus 1, so when we take log of this, you'll be getting 31. So there are actually 32 bits that you need to work on. All right, there are 32 bits that you need to work on. So that is the reason you need to have 32 size things, and 32 size thing is basically, remember, 32 divided by 4, 8 5s. 8 5s are required. That's it. So 5 is represented as 0101, 5 again represented as 0101, so 5 is again represented as 0101, and this goes on. All right, so that is the reason we are doing an AND operation with this. So because all these things have the ones at odd position, so it will only result in a value greater than 0 if the number that we are dealing with also has the set bit at odd position. If not, we'll be getting the result as 0. That's it. So this is a simple code to represent that. First condition to check if the n is greater than 0. Second condition is to check if there is only one set bit or not. This can be checked by doing an AND operation with n minus 1. If in case it's not resulting as 0, that means there are more than one set bits, so we'll be returning false from this condition itself. And the third condition is to check that if that particular set bit is at odd position or even position. If it's at odd position, then n end with 0x8 5s would result in value which is greater than 0. If not, if it's resulting in something like 0, that means the set bit is at even position, so we should return false in that case. Only if these three conditions are met, then we could say that it's a power of 4. It's a pretty simple question, but the thing is, we could learn some concepts like bit manipulation concepts. These things would be very much useful in your competitive programming journey. All right, so if there are any doubts, feel free to comment that out in the comment section. And this is all for it. So thank you for watching. Stay tuned. And for we'll even submit this code. Sorry for forgetting that. Okay. So yeah, it worked. And for your reference, this codes and C++, Java, Python are also attached in the description. You can check that out. Like, this is a very basic thing, and but still I put all the language codes in the description. Okay, so yeah, thank you for watching, guys. Stay tuned.